Hi, everyone. Thank you for being here today for this session. I hope we will have another good time exploring edge computing with its fascinating solutions. Series of sophisticated approaches, particularly for data sharing and intelligence. I'm Yeghisabet, but it's hardly pronounced by foreigners as Elizabeth. Facilitates citizen to government relationship. This is actually certificate authority of the Armenia supporting digital transformation. So this is like IT department of the Armenian government. And we promote digitalizing solutions, everything with AI, with automation, with programming. We have a nice and solid group of programmers and young developers. So all this that will be presented in this seminar, in this session, is devoted to AI solutions, and AI is all math, yeah. And mathematics is the beauty of the truth. Because I will start with philosophy, because if you speak about artificial intelligence, I prefer to say machine intelligence rather than artificial intelligence. If you wish to implement machine intelligence, adopting human intelligence, we go back to philosophy of thinking. How do we realize the nature? How do we think of the universe? Because the human understanding of the universe is bounded by philosophy of science, and obviously cannot encompass the universe solely by approaches such as rationalism, empiricism, pragmatism, or other isms, or the Kantian synthesis. We have other point of view, like Henry Poincaré stated that we use rather conventionalism because it is convenient to express the world or to model, to simulate the world by means of this or that physics or algebra or geometries. And we have different geometries. We have no single geometry. Yeah? We have Euclidean or non-Euclidean. We have physics, Newtonian mechanics, and quantum mechanics that contradict each other. Yeah, because they are motivated and they are implemented for different models. And human understanding is limited with these concepts. So we need a newer science of mind to put our brains into the machine. And we go back to philosophy. And we have Pythagoras that stated that life is well structured. So what this means that everything, maybe it is predefined, we cannot state it, but this is Pythagoras' slogan. And another famous doctrine that also is fascinating, that he believed that numbers themselves present the universe, and the universe itself is encoded by integers whose constituents are prime numbers. So having all this done in our mind, we can try very, very carefully to penetrate to human intelligence, to map it into machine intelligence. But revenons à nos moutons, yeah, like Molière stated, because we come back to our session. Real-time information systems impose deadlines for producing logical results, because information systems vary in their roles and goals. And for especially real-time information processing systems, we need faster and secure solutions. For such systems, provision of proper transactions depends on not only their logical correctness, but also on operability in the required time. Otherwise, these solutions and results will be useless. Edge computing suggests splitting and sharing data between network data centers and local computing power. So we have at least 2 levels in computation. This implies embedding strong authentication techniques to ensure confidentiality, integrity, availability of the shared data and splitted data. Computing within the network partially takes place near the physical endpoints. And this is the case when edge computing paradigm comes into help. So this is for the introduction of our work. So paper outline. The paper is organized as follows. Section first is the introduction, briefly presenting state of the art in cloud computing. And we have traditional cloud mainly for warehousing and processing, not time-driven data. We have backdoors in cloud computing, besides all the advantages of cloud computing, but we have drawbacks. Data leakage or theft, especially in shared environments. And taking into account this, we need for newer, timely, and secure computing. Section 2 presents a brief review of related works in the field. Section 3 briefly describes the edge infrastructure and edge computing paradigm. Section 4 presents our approach, data intelligence at the edge level. And summary of the paper will present key takeaways. This is given in section 5. With all due respect to the authors, I will not pronounce the authors' names, being scared of mispronouncing them. We highly appreciate the work they have done. So I'll present their work by numbers given in the reference list. And indeed, huge work and very, very sophisticated solutions were proposed up to date. And we have added some another vinegar and oil to these solutions. As authors in the first paper state, while provisioning resources on demand and permanently optimizing resource allocation, anyway, timely requirements affect data intelligence related to methods and tools for integrating and classifying real-time information collected from IoT smart devices. IoT stands for Internet of Things. Smart devices, smart cities, smart whatever, intelligence. Given the unpredictable nature of the devices, the authors in the second and the third papers propose applying coding theoretic techniques to provide resiliency against noise. Like we know we have uncertainties in data, we have missed data, and much more filtering techniques and in other intelligent techniques should be applied to recover the missing details. The authors in 4 claim that edge fog computing emerges as a novel computing paradigm that allocates resources in the proximity of the IoT devices and proposed a weighted cost model to minimize the execution time and energy consumption. Meanwhile, in order to address IoT applications heterogeneity, a lightweight pre-scheduling algorithm to maximize the number of parallel tasks for concurrent execution has been suggested. In the 5th, the authors introduce a survey on multi-access edge computing architecture and propose an elaboration of the cloud computing platform via the deployment of storage and computational resources at the edge, thus reducing latency of edge devices and utilizing the core network more efficiently. Authors in 6 rightly state that cloud and edge for computing are non-interchangeable technologies, and they cannot replace one another. But when combined, they can contribute to promoting hierarchical data infrastructure and layered data processing. In the 7th, authors interpret fog edge computing to be the future infrastructure on IoT development and an important computing paradigm in realizing the intelligent cyber-physical world. Authors in paper 8 highlighted typical security issues in edge architecture. Besides, they explored security algorithms acceptable for governing IoT data privacy, taking into account the resource-constrained nature of the devices. Particularly, elliptic curve-based cryptographic solutions were selected as most appropriate. The authors in 9 stated that understanding and implementing edge computing implies consideration of traditional computing paradigms, exploration of which can orientate the developers in selecting and combining relevant approaches. The authors in 10, 11, and 11 mine assert that besides the well-known methodologies in computing, trusted systems development requires embedding confidential computing, which preserves the data and confidentiality not only in the rest and in transfer, but also in use when you process. So you process encrypted data, not plain text. This is called as confidential computing. Shielding the sensitive data, also the whole set of applied programming techniques from the rest of the entire system makes the data being processed to become accessible solely to authorized programming codes. The rest of the related works is devoted to rather supporting approaches for developing intelligent computational systems. Computing is the process of using a technology to complete a given goal-oriented task. Most of cases, we combine different paradigms of this listed here. This is not a complete list. We combine different paradigms in one solution, as large-scale computing mostly involves a series of approaches. Indeed, while looking through different styles, developers may adopt and adapt relevant concepts from other paradigms in order to best achieve some computing. In edge computing, data and computation are closer to network devices to improve response time and save bandwidth. In this sense, edge is an optimization of cloud, in that it moves computing to the source of data, to the edge. Note that edge computing is preferred over cloud computing in remote locations when there is limited connectivity to the centralized cloud. These locations require local storage, a mini data center to process time-sensitive data, and edge computing provides perfect solutions for it. Also, edge computing is beneficial to specialized and intelligent devices. These specialized computing devices respond to particular needs in a specific way. Edge computing architecture is still a three-tier network. The very basic level in this hierarchy outlines the edge level network where network devices and sensors reside. The second layer deploys the edge data centers, which perform the operational management of edge devices. We propose regrouping the devices according to their computational mission. Classification of devices prior to inclusion to some group may be performed according to their inherent level of intelligence. The main cloud server still is on the top of the hierarchy. This segmented architecture of the cloud edge enables splitting the overall workload while leaving some portion of data processing at the basic layer of the network, closer to the devices. Note that edge computing shouldn't be confused with autonomous computations and data processing embedded in these very devices. Edge computing paradigm stands at the intersection of 5G, artificial intelligence, and digital transformation, and is already used all around us. Traffic lights, indicators on digital planes, autonomous vehicles, smart cities, telemedicine, augmented reality, AI virtual assistants, video monitoring, gaming, etc. To list just a few. We can't get the data closer to the data center, so we will get the data center closer to the data. This way, edge computing redefines the infrastructure of the entire network. Key features of data computing is extreme wireless. Also, it can facilitate constructing and maintaining cognitive networks with the capability to map human intelligence into machine intelligence. Edge architecture eliminates the necessity of allocating individual bandwidth for each device on the main cloud. Introducing the additional layer will solve a series of issues by adopting the so-called data minimization principle. So according to which the amount of data being sent to the main cloud should be minimized while keeping the whole chain of the data under control. The main cloud still plays its own role in big data analysis, business logic maintenance, and data warehousing. We came to our approach. Data intelligence at the edge refers to analytical tools and methods used to derive information from the collected data and focuses on analysis and interaction with information to promote better decision making. Data intelligence applied at the edge level concerns, but is not limited with the given concepts. The paper focuses on operating deliberative AI agents and introduces a selective approach for intelligent supervision of real-time AI systems, regrouped according to their intellectual mission. For this scenario, relevant expert systems, each designated to respond to specific queries, is recommended to be deployed on the main cloud level, where historical experience in terms of the knowledge base is stored and gets updated. Also, the overall data analytics is conducted. So we will refer to data splitting, sharing, and privacy concerns in edge computing architecture. Particularly, timely management of self-organized collaborative computing agents implies developing a semantic graph model for agent machinery and the system abstract architecture. An implementation of such a graph can be found in my recent paper. Last year, I reported in Los Angeles. Here, computation is performed over relevant pieces of information having two qualities, value and weight. The deductive logic is constructed on the strict logical arguments reinforced with the specified rules of inferences over premises and conclusions. Activation within the network depends on the weights. Reasoning based on 0 first, second, and even higher order logic assumes involvement of non-supervised machine learning methods and techniques implementing facts, relations, and rules. Mathematical background for machine reasoning can be found in the paper 13. Particularly to support declarative statements having either of two outcomes, true or false, zero-order propositional logic may be constructed as is illustrated. For instance, if we wish to implement group, algebraic group, we can implement this way with facts. What is the group itself? Is an abstract algebraic structure supporting one single operation, yeah? And this is associative. If we wish to express this human logic, logic of the mathematician into the machine, we can translate it into this language. So this the mapping of human thinking mathematically to machine thinking. And each property is clearly stated. It's a group, and it is closed on the sum operation. Closure means whatever you combine, it doesn't leave the set. Then we have association. Associate will also regrouping, parenthesizing gives the same effect. This is not a good property in cryptography, but for groups, it takes place. So we have unit. So this is a reversible in an invertible algebra. In cryptography, we escape from invertible algebras. We go to non-invertible algebras to insert secrets, to make the computations harden, to stop the brute force attack, and so on. But this is just an example how we can put intelligence into the machine and how we can use Python language to express these things. And first order logic, also known as predicate logic, is an extension of the propositional logic and involves quantifiers, like we see, for every piece there exists such thing. So we involve other relations that is not a zero level logic phase. We jump to higher logic phase. And for instance, how we can express functions to be a special kind of a binary relation. For every element in the domain, there should be some element, some mapping, some image in the range that this function takes place. So this is the way how we can express our logic. Knowledge representation in AI agents combines objects, relations, and functions via symbolized reasoning. Key instructions are partitioned into well-defined subjects and predicates with a strict restriction. Predicates refer to single subjects. For instance, given a sentence, vehicle is a subject, decrease is a predicate, and speed is the value defined by the predicate. Reinforcement learning will be the best mechanism to train deductive agents situated in an environment and to simulate machine reasoning. The gathered skills are absorbed and assimilated as follows. So this Python code, how we can express this. These are what's. So what should we do? These are functional requirements, and how it is done, it is on the deeper level. But this is just the case how it can be expressed our thinking programmatically and on the machine. Mini data centers endowed with local strategy patterns, each operating separate groups of devices with similar intelligence, will react to stimuli faster and according to specific needs. Urgent medical diagnosis, traffic control, border security, and other timely computations utilizing machine intelligence can certainly benefit from edge computing. Meanwhile, historical data and relevant expert knowledge will reside on the traditional cloud, being queried on demand. Data splitting is the act of partitioning available data into portions according to some well-defined criteria. Generally, splitting is done to perform preprocessing prior to model construction and may contribute to parallel computations, segmentation and pattern recognition, cross-validation when one portion of data is used to run a specific computation to validate another portion of data. Secret splitting and threshold scheme construction like Shamir, Blacklane, or other algebra-based and hierarchical computing. Data within a device are under sole control and are of a required physical and cyber security. In this sense, the edge level must ensure the confidentiality and integrity of data being shared or exchanged in order to exclude exposing data to unauthorized access. As in edge computing, some portion of data are shared with the main cloud for a deeper and probably latent analysis. The edge level may even split and share cryptographic keys, tokens, and other cyber identifiers in order to keep trace of the shared data between computational and storage levels. The hierarchical nature of the edge computing paradigm points out a series of sensitive aspects that should be addressed, particularly while splitting is done within a specific edge data point and still under the sole local control, sharing data parts results in transferring them. And this is when solely GDPR compliant solutions have to implement it. GDPR stands for General Data Protection Requirements, accepted in Europe. So we refer to eIDAS, electronic identification and authentication techniques. The European Union's dictates. And the volume of intelligible data that needs to be shared should be minimized. Here, the data minimization refers to encrypting data, thus making their content inaccessible for non-authorized access. As a result, the amount of available and intelligible data consequently decreases and resides in the scope of confidential computing. Data privacy at edge is of another great importance and should be well explored to ensure confidentiality, integrity, and availability of information in the hierarchy of the network. For instance, most of cryptographic operations may be delegated to edge servers. Besides typical encryption algorithms and collision-free cryptographic hash functions, it is recommended to embed mechanism of searchable public key encryption, fully homomorphic encryption, honey encryption, and AES 256. Identity management ensures automatic identification and authentication of edge devices and relevant edge computing resources. For this purpose, besides well-known approaches given on the left, we propose embedding the following mechanism at the edge level: hardware-based tamper-proof storage devices, HSMs, hardware security module; secure cryptographic key generation, data and key encryption, key storage and backup; also verifiable secret splitting and sharing, where splitting and verifying both are validated by solving a non-reversible function. Non-reversibility, how does the attacker work? In that she cannot verify own success or failure during the attack iteration, as there is no public key or private key pair to check the validity of the experience. Yeah, because even failure gives you much more information. You won't go deeper to this way. Yeah, you'll change your strategy, but it also helps to move forward to promote sophisticated attack. Whenever appropriate, timestamp may be embedded. A timestamp is a mapping, as it is illustrated, and this programming code is real Java implemented in our company. It stops the replay attacks, because the computations, when done at the edge level and store some result on the cloud level, they will be validated according to the time, at which precise day and time this operations was performed. And the Java format timestamp string example is given at the bottom. So this is a real result for programmers. It is well known that blockchain is a digitally distributed, decentralized public ledger that exists across the network. No single entity controls the blockchain network. Anyone can join at any time. Blockchain identity management systems are commonly used to address identity issues such as data insecurity and fraudulent identities. The distributed ledger will store labeling of the classified data and their cascading aggregation, validation, classification, and then filtering. And then complete paths, individual or joint, depending on the implementation, for each device having data shared between the edge and main cloud levels. Due to resource constraint nature of IoT devices, we propose constructing the edge to main cloud blockchain based on secure computations on embedded secret elliptic curves, reversing the which without the knowledge of the curve itself is known to be an NP-complete problem. Unlike the simplified curves used in traditional encryption, we do not simplify the Weierstrass equation. Scaring, yeah? We use original curve and keep it secret in our HSM. And recall that elliptic curve over the real numbers is defined by Weierstrass equation, the scaling curves. And if you keep it secret with zero determinant, so this shouldn't be singular curve, should be a real reversible curve for legitimate users. And usage of elliptic curves eliminate classical proof of work. If you remember with Bitcoin mining or other currency mining, you should have proof of work. Yeah? It's a heavy, very heavy computation that proves the legitimacy of the entity. We introduce a lightweight proof of work, meanwhile keeping the computation and identity management still secure. And it will work for the two levels. This is the process, how we encrypt, hash, and how we create the blockchain from the edge to the cloud. And this will strictly identify the endpoint device, own computation, own share on the main cloud, and impersonation stops completely. How about cryptographic key management at the edge? The amount of information protected by a given key should be minimized. The amount of exposure, if a single key is compromised, also should be minimized. Note that edge level encryption secures the data collected from edge devices such that no level in computing receives the raw version of the payload directly. For effective and secure key management, HSM and related secure zone at the edge level should be embedded. This will ensure supporting sensitive operations like it's listed on the slide. In order to support two-level cryptographic key sharing, the edge-level HSM internally should perform cryptographic key generation, key encryption applied AES 256, cryptographic key verifiable secret splitting. One portion of the encrypted key remains at the edge secure zone, while the second portion is transferred to the main cloud, but encrypted. Each time a transaction is activated on the main cloud side, firstly, a verification of the validity of the key share is performed. Most of existing secret sharing schemes of proof of security like Shamir or Blacklink are based on the assumption that all participating users are legitimate. This approach is prone to sophisticated impersonation attacks. The attacker can impersonate a legitimate party without being detected even. Schemes of proven security are referred to the papers 15 and 16 of the related works, where the impersonation attack is advised to be blocked based on modification of Shamir's threshold scheme, or based on plain parametric curves with one parameter representation for a master key, respectively. Other solutions are arising from Latin squares, also referred. So what we propose? We propose constructing a verifiable secret sharing scheme based on abstract structures from non-associative algebras. Quasi-groups are modifications of groups, and they eliminate associativity. It is very bad for cryptography as well, because if you regroup your computations A plus B then plus C, and it equals A plus B plus C, this association lightens the attacker work. So we escape from commutative algebras, from associative algebras, to make them irreversible. And we eliminate the identity element. If you have no identity element, your algebra becomes non-invertible. And the attacker should look up the tables, trying every combination, and it will take to numerical explosion. And no computational power will be sufficient to convey this type of attack. So our proposed scheme works on the quasi-groups. I won't go deeper into this algebra because this is another scaring algebra, but this is our approach. And we came to conclusion. Our paper presented a series of methodologies which can be efficiently implemented in edge computing. By combining relevant computing paradigms and secure data processing, the proposed approaches can reinforce timely and intelligent computing within the edge cloud hierarchy, where data chaining and logical linkage is achieved by embedding blockchain through verifiable secret sharing. That's all. Thank you for patience. You're listening. I'm open to answer to any question.